Welcome everyone to our first of two videos on stoichiometry. In this video, we are going to look at the relationships in a balanced chemical equation and understand how those quantities are related. That will lead us into being able to do a lot of very useful things with a chemical equation. So this word stoichiometry, which we often in chemistry just say stoich, it comes from two Greek words, meaning first stoichion, which means element, and metron, which means to measure. So any word in science that ends in metry, geometry, as an example, they all are dealing with measurements. Okay, so here we are measuring the chemical elements. Now, here's our real definition. Stoichiometry is the study in chemistry that deals with calculations. It could be volumes as well, but typically the masses of reactants and products that are involved in a chemical reaction. Our previous lessons have been looking at relationships between the ratio of elements in a chemical compound, specifically looking at the chemical formula. Now we're going to look at chemical equations and looking at what the ratios in a balanced chemical equation tell us as well. Let's look at this reaction here, which is the synthesis of ammonia, NH3. The balanced chemical equation tells us something very specific. It tells us that one molecule of nitrogen gas will react with 3 molecules of hydrogen gas, and that will produce 2 molecules of ammonia, NH3. The balanced chemical equation is telling us a ratio in which the reactants combine in which the products are produced. A chemical equation is the simplest whole number ratio in which this occurs. However, if we have more molecules reacting, these chemicals will still react in the same ratio, and the ammonia will be produced in the same ratio. So let's take a look at an example. So just written up the same thing here, but what if we doubled the amount of a nitrogen gas which we were reacting? The key idea here is that chemicals will always react in the same simplest whole number ratio, so that the law of conservation of mass and the law of definite proportions can be maintained. So if we double the amount of nitrogen gas, what's going to happen? Well, if we double the nitrogen gas, then we're also going to need to double the amount of hydrogen gas. So 2 molecules of nitrogen gas will require 6 molecules of hydrogen gas. And now we'll produce twice as much ammonia. We'll now produce 4 molecules of ammonia. Note that the ratio, a 1 to 3 to 2 ratio, is still maintained. The only difference is that all quantities of each particle involved in the chemical reaction have been multiplied by 2. Well, even though a balanced chemical equation is dealing with small quantities of individual particles, in reality, we are almost always reacting huge numbers of molecules and atoms. So let's scale it up a bit. What if we wanted to react those chemicals and produce 2,000 molecules of ammonia? Well, here's our balanced chemical equation. If we want to produce 2,000 molecules of ammonia, The balanced chemical equation tells us that we will need half that number of particles of nitrogen. So specifically, we will need 1,000 molecules of nitrogen gas. If we need 1,000 molecules of nitrogen gas, the balanced chemical equation tells us that we'll need 3 times the amount of hydrogen gas. So that will need to react with 3,000 molecules of hydrogen gas. So note that the ratio has been maintained. 1 nitrogen to 3 hydrogens produces 2 ammonia. 1 to 3 to 2. Now, 2,000 molecules, as we know, is actually not a lot of molecules. What we really want to do here is scale this way, way up to the quantities in which we react on a macroscopic level, something that we could actually weigh and experience in a lab. Now we're talking. What if we wanted to react 6.02 times 10 to the 23 molecules of nitrogen gas? Well, I've done the calculations for you. If we want to react 6.02 times 10 to the 23 molecules of nitrogen gas, we will need 1.806 times 10 to the 24 molecules of hydrogen gas. And that'll produce 1.02 times 10 to the 24 molecules of ammonia. So now we're on the scale that we will experience, because that number of molecules is getting to be something that we could mass and experience in the lab. However, the quantities that we're dealing with are so huge that we need to simplify this a bit. So let's start off by looking at this. Those calculations I did were just multiplying the moles of nitrogen gas by the ratio in the balanced chemical equation. Nitrogen and hydrogen react in a 1 to 3 ratio. So I multiplied the molecules of hydrogen, or I multiplied the molecules of nitrogen gas by 3 to get the molecules of hydrogen. To get the molecules of ammonia produced, I multiplied the molecules of nitrogen by 2. So I'm still doing the same mathematical operations, but just dealing with huge numbers. Now, 6.02 times 10 to the 23 molecules is a pain to deal with. But as we know, there is a way we can simplify that quantity of molecules. We can use the mole shorthand, because we know that 6.02 times 10 to the 23 molecules is just 1 mole of molecules. Remembering the term mole, or the quantity, 1 mole, refers to that specific number of particles. So let's just repeat the question and replace that huge number of molecules with a quantity of moles. So another way of asking the same question is, what if we wanted to react 1 mole of nitrogen gas? I'm changing the language, but I'm not changing the question. 1 mole of nitrogen gas will react, 3 times 6.02 times 10 to the 23rd. That's just 3 moles of hydrogen gas. 2 times 6.02 times 10 to the 23 moles of ammonia is just 2 moles of ammonia gas. So we've simplified the language here and still are talking about huge number of particles. 1 mole of nitrogen will react with 3 moles of hydrogen to produce 2 moles of ammonia. That same ratio with the same numerical values as we see in the balanced chemical equation. So even though the numerical coefficients in a balanced chemical equation are the number of individual particles which are reacting, because of the definition of the mole, they can be interpreted as mole ratios. And in fact, because we never deal with individual particles, we are always going to refer to those coefficients, the numbers in the balanced chemical equation, as mole quantities. 1 mole of hydrogen reacts with 1 mole of nitrogen reacts with 3 moles of hydrogen to produce 2 moles of ammonia. And the reason for that is because those are quantities in which we can react in a normal basis. The most important thing about this concept is that because of this ratio, if we know the number of moles of any one substance in a balanced chemical equation, we can determine all the other quantities needed to react or be produced. And we are going to do that in part 2 of this video, where we're going to solve mass-to-mass stoichiometry problems.